Okay, so let's start off with what is being asked of us. It says, curved arrows are used to illustrate the flow of electrons. Using the provided starting product structure, draw the curved electrons pushing arrows for the following reactions or mechanistic steps. Be sure to account for all bond breaking and bond making steps. Okay, so we know that sodium amide amine is going to be what we're going to be starting off with. So in other words, this guy already has a minus charge that's going to be associated with it, right? It's going to have a minus charge. So what do we know about compounds that are going to be negatively charged? Are they going to want to give up their electrons, or are they going to want to be receiving electrons? Yeah, so they're going to be the electron donors in this case, right? So if they're going to be donating electrons, so we can actually show that electrons are going to be moving from them to where? Where are they going to go? On the what? On the hydrogen, that's correct. So these electrons here, let me put it in a different color. Pink. These electrons, there's two there. One is hidden under my drawing. Okay, so they're going to go to the hydrogen. Okay, and then that's going to do what? What's going to happen to those electrons? The electrons that were on that hydrogen or associated with that hydrogen. Well, let's look at this guy here, right? This is sodium amine, okay? So sodium amine. So it's going to have it was sodium amine, but we removed the electron, right? Or the sodium part of it. So the sodium is going to have a plus, the amine is going to have a minus charge, right? So, but the reason why it's going to go to the hydrogen is because the only thing that's going to be willing to accept the hydrogen, there are going to be two possibilities, right? So, or a couple of possibilities. You have all of these hydrogens, or you have the bonds, right? So if you're a negative charge and you're going from a negatively charged amine, chances are you want to become ammonia, right? Okay, so that means that you're going to have to get to the point where you're more stable, which is to have a hydrogen there. And so if you have a hydrogen there, so you're basically just taking that H plus and it's coming over here to kind of act as that last leg to it, then what has to happen to the electrons that are on that hydrogen? So they go, so they'll actually go to the carbon and then move to that bond and then move over to here, right? So, okay. Now, if they go to there, then that means that our product, our intermediate, did I screw up? Yeah, I didn't. That is a horrible drawing. Can you guys see it at home?
Yes.
Yep. Yes.
And to kind of address that, remember at the very, very beginning of the semester, last semester, we were talking about electron acceptors and electron donors, right? And so this is where we're going to be playing at. So we got to pay attention to what is going to be our proton acceptor and which one is going to be not a proton acceptor, our electron acceptor, and which one is going to be the electron donor, right? So in this case, we know that since this guy is a negative charge, it can donate those electrons, okay? So then your options are, we know that if it's an SP molecule, that guy is usually a proton acceptor or donor. SP, let's say an SP molecule, is that going to be a proton acceptor or donor? Usually. Electron acceptor or donor. Is it? Triple bond. So if you have a triple bond, does that guy usually, is it usually gonna donate? Because is it going to be able to sit there and make a quadruple bond? Right? It's not. So we know that it's never going to be able to make a quadruple bond, right? So it'll never accept electrons. It'll donate electrons, right? So we know that this triple bond isn't going to donate the electron. So what's going to be able to accept the electrons, in this case, is just that carbon at the end, right? And so then you'll be able to free that hydrogen, right? So then that hydrogen is free, and then you're going to end up getting ammonia formed in this case, right? So you're going to have an ammonia byproduct, okay? So then, after we get that guy, yeah, this is a little bit better, but still kind of crappy, right? So this guy here is going to be basically, all this guy is this guy here, right? And then all we've done is put the electrons on the carbon, because that's the only one that's going to be able to hold the electrons, right? And so now you have a negatively charged carbon. Negatively charged carbons are called, if it's positively charged, it's a what? And if it's negatively charged, it is, so it's carbo and anion, okay? So we have this negatively charged anion, and we still have, oh, sorry, did I skip something? We have, I did, CH3 Br. Okay, so now we're adding CH3Br to our mixture, right? That's the second step. Okay, so this is a multi-step reaction. So in this case, the second step, we're adding methyl bromine or methyl bromide. So methylene bromide. So we're adding this to it. So in this case, who's going to be donating the electrons? Who's going to be my electron donor? Who's going to be giving away the electrons? The carbo anion. So we're going to take these electrons from here. Right? Because we know that this guy isn't all too happy to be like this, right? So it's going to be anxious to get rid of those electrons. So who do you think is going to be the electron acceptor? Look at your product. Yeah, your bromine, right? So your bromine. So then what we're going to do is, first off, we're going to act on the carbon, right? It's going to go to that carbon first. And then it's going to go from that carbon to break up that bond to allow bromine to live on its own, right? So then bromine is self-sustaining, and we get this product, okay? You had a look. So always look at the one who is uncomfortable, right? So we know that ammonia is NH3, right? So if you have NH2 minus, then you're like, oh, that's not kind of cool, right? That's not something that we see commonly, right? So that's probably going to be my starting point. That's going to be the guy who's going to start the chain of events to happen. You always need somebody to get us started, okay? So, and you guys know enough about chemistry that, okay, what are some of the common molecules that are stable, right? Because it all deals with stability, right? At the end of the day, it's all about stability. And then the other thing is just, you have to go through the flashcards and remember, oh yeah, it'll start clicking the more you see it. If you don't look at your cards, if you don't do any of that, then you guys are not going to get to that step where it starts sticking up here. And it does, it just takes, I hate to say it, it takes you looking at your cards. You should be looking at them daily, you know? So, and this is the 2 steps. This is 2-step reaction, right? So this is when we're starting to get into multi-step reactions. Okay, so questions? Concerns? Sure. 75? 65. Okay. So I'm just skipping all over things, huh? So 66 is look like this. Let me make sure I have the right one. So it's like a benzene ring. Okay, don't make fun of my drawing there. Let's try it. We will see. Problem is that there's too much, there's a lot to the problem, right? Too many steps. So we're gonna have to do it piecemeal. Okay, so where are we gonna start? What is gonna start off donating the electrons? Nope. That's not where you're gonna start from. You need somebody, because this guy, it has a plus charge, right? So this guy is obviously gonna be, is it gonna proton acceptor? I mean, electron acceptor or electron donor? Acceptor. So it should be accepting electrons, right? So first off, we got to get somebody who's going to donate those electrons. The triple bond, that's right, not the water. The triple bond is going to be the donor. Water is kind of stable. It's going to be cool unless you get something to get it started too. So in that case, we know that the triple bond is going to be the one that's going to initiate it. So we start off. Can you guys, hold on. Screen 2. Yep. Okay. So these guys, so it's gonna, actually what's gonna happen is gonna be this. Like this. Okay, so the electrons, again, so triple bond, because it's sp3, I mean sp, it's an sp, it's going to have that ability to donate those two electrons, right? That could then cause this hydrogen, right, to kind of dissociate, which will cause, so we'll have this happening on the hydrogen. So it's attaching to the hydrogen. Then the hydrogen will come here and donate its electrons to the oxygen, right? So then as a result of that, we're going to end up with water, because then that we have those two electrons that are going to be on top of water, right? Are you with me so far? This guy is going to end up with a plus, right? It's going to take that hydrogen from over here and associate it with that. So you end up with two hydrogens. Okay. So then, now that we have water and we have this guy plus, Israel, you have these electrons where what's going to be the next step. So that's the only step here. The next step in this case with the water. Because now we have a carbon cation. So is that carbon cation, is it going to be an electron acceptor or donor? It's going to be an electron acceptor. So who's going to be donating the electrons? Now, over here, water. So we're going to take electrons from water, and then it's going to it's going to go towards that cation, right? So then we're going to end up with another hydronium ion is going to be added onto the mix. So now we have the water molecule that's attached, physically attached to that cation, right? And so now we have a plus there, right? So what's going to happen here? Who's going to be my electron donor and who's going to be my electron acceptor? Okay, so water again is going to donate. Okay, so then that's going to be acting on the hydrogen. Okay. So now that we have it acting on the hydrogen, the hydrogen is then going to provide its electrons to the oxygen. Okay. So then we're going to get, as a result, our product. So we're going to end up with our ammonium ion, and we're going to end up with an alcohol, right? Or anol. Okay. 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 So now, what's going to happen here? It's going to be my donor and my acceptor. Look at the outcome, the products. Okay, so we're going from like nothing wants to work. What was that? Okay, look at the outcome here. So now we have a plus here, right? And then this guy is just OH, everything seems hunky-dory, right? We have an anol. Okay, now the anol is getting a plus on it. So what do you think is happening there? Oxygen is going to be losing an electron. So here, you have your electrons that are going to affect this. So it's going to be transferred to the bond. Then, as you were saying, the double bond is then going to transfer to the hydrogen. The hydrogen is going to transfer to the oxygen. And so we're going to end up with water. And then this is going to end up with a plus. And then also we have our double bond being changed from here to there. You guys remember what that's called? Where we're moving our double bond. So our double bond is no longer here. It is now here. I mean, that's essentially what you're doing in this case is a hydrogenation, but there's a little bit more. The fact that we're basically transferring our double bond to here. So this process of going from, let's say, from this anol to, what is this called? What would be it's a ketone. What is that called? The process of going from anol to a ketone.
Tautomerization.
There we go. She says tautomerization.
Yeah.
Tautomerization. So that is correct. That is correct. Okay, so now we got this guy, right? And then how are we going to get from our plus here to our, how are we going to get rid of our plus on the oxygen? Where are the arrows going to go? Okay, so our water is going to provide electrons. Okay. And that's going to go on to, that's right. Then the hydrogen is going to go to the, yeah. the bond, and then we end up with just our double bond, this guy, and then we end up back with our hydronium ion. Yeah. So in a sense, well, it's an exchange, right? So the hydrogen is now a plus. Now it's able to attach to the water, right? So it's just picking up or the hydronium ion is picking up that H plus. Okay. So part of it is look what your products are. So if you know what you're starting with, what you're ending with, try to figure out who's going to be donating the electrons, right? Where can you get the electrons there? Here, I mean, it's kind of clear that they want you to use the water because, hey, guess what they're showing? They're electrons, right? They're available, right? And somebody has to start it out. Somebody has to donate the electron, right? If it has a plus charge, they're not going to start it out, are they? No. They're going to want to receive it. Okay? Does that help? Did it work? Or am I giving you the totally wrong answer? Okay. Okay. So again, if you look where you're starting from and where you're going, it's going to help you out in that process. Okay. Give me 1 second while I pull up. Can you guys see that? Can you guys at home see that? That's the important thing.
Yeah.
I know they
see the slide.
What was that?
We can see the slide.
Okay, good. You can't or you can?
We can. Okay,
good. Okay, so last we were talking about strong acids versus weak acids. And then we got sidetracked and we were talking about pKa's and how pKa's can be a reflection of how strong an acid and weak an acid is, right? Okay, so we're back there and we showed us how to do the calculation. So you need a strong base to remove hydrogens. So in this case, to remove this hydrogen, we're going to need a strong base. So this guy is going to act as a strong acid. Okay. So this was, remember we were just talking about the amide ion just a few seconds ago. Well, we got ahead of the game, right? So this is where that amide ion. So that amide ion isn't going to be stable. So we're going to be removing that hydrogen from our hydrocarbon, okay? And that's what basically happens here. So if we remove the hydrogen from our hydrocarbon, now we have an acetylide ion. Acetylide ion. Okay, so we have an acetylide ion, which is now going to be our weak base, and we have a weak acid. Okay, so here ammonia is acting as a weak acid. Okay. Now, if we have a weaker acid and a weaker base, right? So again, we're gonna have the hydrogen being removed. But the problem is in this case, you're not going to get this formation. You're not going to have that strong acid, strong base. It's favoring the other direction. Okay. Does that make sense? So we know, oh, I'm pointing. Okay. So we know that it's favoring this direction. So you're going to have more of this being present than the other way, right? So that suggests to us that, again, the hydroxide isn't going to be strong enough base to sit there and cause the hydrogen to be pulled off. Okay, so you're going to get this more of this forming than this product, where in this case, the amide ion is going to be strong enough to drive the reaction so that we'd end up with the ammonia. Does that make sense? Okay, and again, the arrows, look at the arrows. The arrows are letting us know it's favoring going towards the ammonia and the acetylide. Okay. Okay. So when we're when we're looking at trying to form, let's say, expanding onto our carbon chain, right? So often we'll use reactions where we're using the acetylide ion and a alkaline bromide, halide, okay? So here's our alkaline halide. Here's the acetylide ion. Okay, so in that case, we're going to get the formation of, and this specifically is going to be 3-heptine. So in this case, we're just adding a carbon chain onto the triple bond because the acetylide is going to be able to accept it. Because if you look at it, the bromide is going to have that negative charge, right? This guy is going to have like that positive charge, then that's going to allow it to be accepted. Okay, now it's not going to be quite like that because really all that's happening is the electrons are being transferred. Okay. Okay, so the way that this process is called, this is an alkylation reaction. So in this case, your electrons are going to be transferred from the acetylide to the carbon that is attached to the bromine or the bromide. And then it's going to transfer its electrons, it's going to disrupt that bond and transfer its electrons to the bromide. So the bromide is going to end up with a negative charge, and you're going to end up with the hydrocarbon just adding on the other chain of hydrocarbons. Okay. So alkylation, alkylate alkalization is just the addition of your hydrocarbon. Okay, so like if we went hydrogenation, right, that means you're generating hydrogen, or you're adding hydrogen. Okay. Here we're just adding an alkaline group. Sorry. Okay, so this is the one that we kind of showed in the homework problems. So here we have 1 pentyne. So we're adding sodium amide. And then the amide is going to end up causing the 1 penthyline ide. And then that's going to be, then we're just going to add the alkaline group, the alkane, to the end of that. Does that make sense? Or am I confusing you as much as I'm confusing me? So we know that, take one step back. This process is just the addition of an alkane or an alkene or alkyne, okay? So an alkyl, right? Then the first part is just making that acetylide, okay? So we're just giving this guy a charge. So that's that first step. Step 1 is to make the charge, right? So then we have a negatively charged alkyd, okay? So then that alkyd then is able to accept the hydrocarbon. Again, I'm drawing on my screen. You guys are not seeing anything that I'm drawing, right? Okay, so this first step here is just to make the acetylide, okay? So in other words, this guy, ide, negatively charged, right? You guys remember that? Chemistry, right? Basic chemistry, ide, negatively charged. So we got a negatively charged ion, right? Now this acetylide then is now primed to accept this alkyl, right? Or an alkane, alkene, alkyne, right? Now, but we know that the bromine is going to end up at the end of the day having going to be Br minus, okay? Where it's filled with all of those valence electrons, okay? So, but all you've done is just you've added on those carbons to the end where that negative charge was at. That's all that's happening. Okay, so we know that this process is called, I keep misspelling it, Alkylation. Okay, which just basically means adding on hydrocarbon. Okay, so that's all we've done. So it's a two-step to add on hydrocarbons to a triple bonded molecule. Are you with me?
Yes.
Okay, simple, right? Not too hard. So first step is to cause that the triple bond to actually form an ion. So we're going from a stable triple bond to form an ion, step one. And so what do we use to do that? What are we using to do that first step? I'm asking you. It's a question. What do we use to do that first step? Sodium, no, not ammonium. Sodium amide. Okay, so we're using sodium amide for that first step. Sodium is just to bring the amide to the party. Amide is doing the job, right? So the amide causes the triple bond to get a negative charge, and it's going to form an acetylide. Okay, so then that acetylide then is going to interact with a alkaline bromide or an alkaline chloride or an alkaline fluoride, right? And then it's going to just add what was attached to the bromide to the triple bond. Okay. Okay. So now let's see. So how can we, so you guys remember it. So that's a two-step, right? So that first one causes the acetylide to be made. The second step causes the connection, right? Okay, so how can a compound be prepared from the starting material? So this is our starting material right here. So, and we want to end up with this guy. Okay. So now what we're going to be doing is kind of combining some of the reactions that you guys are already familiar with, right? So what do we know that's going to end up causing ketones to form? What's that? Sodium amide. Will that cause a ketone to form? Well, yeah, we're going to go through that process, but what causes that process to happen? What causes that triple bond to end up forming a ketone? Sulfuric acid, okay. Sulfuric acid, it will do that, right? So we know, and water, right? So if we have sulfuric acid and water, here, we get the formation of our beautiful ketone, right? Because we have this enol, this enol forming, and that's going to end up with the ketone form, right? by tautomerization. Okay, so if we can start off, if we're starting off here, our first step is just the addition to this guy some extra carbons, right? So then we're going to use that first, second, and then we're going to end up with the third step. Does that make sense? So if we're starting out with one butene, then what we're going to need is for the first step, we're using the sodium amide, and that's going to cause what to form again? It's going to cause us the C negative, triple bond C negative, right? Okay, so we call those acetylide, like acylide. What was that? It would be a carboanion. Yeah, that's also a very generic name for it, carboanion. Okay, so then the second step causes us to form the 3-hexene, right? So then once we get to 3-hexene, we know that we can use what Israel was suggesting, use water and sulfuric acid, and then we'll form our anol. And then when we get the anol, we know that tautomerization occurs on its own, and we get our ketone. Okay? So that's the process of using 3 different reactions. First one, the very first one causes the acetylide to form. The second one causes the alkylation. And then the third one causes the hydroxide or the anol to form. And then tautomerization causes the ketone. 3-stepper. Okay. Okay, so if we wanted to go from an ethene to 2-bromopentane, this is a good one. Ethene is 2. So what can I use to sit there and get to 2-bromopentane? Ooh. So this here is called retrosynthesis reaction. So in other words, we're going backwards, right? Backwards, right? Retroviruses are called retroviruses because they go backwards. They start from the RNA rather than the DNA. So retrosynthesis is starting backwards. Okay, so how can I get from here to here? And then how can I get from here to here? And then how can I get from here to here? So in other words, all you're doing is breaking it down the steps. So the very first step is, okay, I have to get the bromine form, right? That's going to be our last step. Bromine, the addition of the bromine is going to be the last step. It makes sense that we're going to end up with a double bond here, because then that would give us our starting unit. Draw this. Again, you guys, you got to remind me that you can't see that I'm writing, because it's working perfect on my screen. Do it like this. So we know that this here, that's ethane. That's 2 carbons, or we could have started over here, but it makes sense to start where the bromine's at, right? So in this case, we're going to end up with double bond. Okay, so do you guys remember where terminal, we've talked about terminal carbons, right? And then the terminal alkenes, right? Meaning that you have those at the very end, right? There's only one way that we can get that. Do you guys remember that? Yeah, no, maybe. don't. It was last week. Okay. So, but we can use the fact that we know that that guy isn't as popular. There's one reaction that can get us there. So if we're going from that, okay, so then the next part is, okay, so we have this guy. Then we know that a triple bond at the very end, right? Okay, so then how can we go from, and this guy would represent our starting unit, okay? So this is working our way backwards, right? So just drawing the structures that you would get to get backwards. And then you just start, okay, so what can I get from this point to this point? So how do I start from a triple bond to a triple bond at the end and these carbons added on? Oh, again, I'm not showing you guys what I'm doing now. Laser pointer. So how can I get from here to here? First part. You guys see that? That's right. So we'll use the sodium amide. And then, so that sodium amide is going to cause the, what to form again? Acetylene, acetylide, right? So we get the acetylide forming, and then we just attach the other carbon chain to a bromine, right? And so that's just going to add a bromine, that chain of carbons to our acetylide, okay? So then we get the formation of that chain of carbons attached to our acetylide, okay? So now we got our acetylide, our acetylene, right? What is this? 1, 2, 3, 4, 5. So that would be pentylene, 1, pentine. Okay, so we got the 1 pentine form, right? So, and then how do I go from 1 pentine to, in this case, we're going back this way. So we're looking at 1 pentine to 1 pentene. Well, we know that the one way of doing that is by adding hydrogenation, right? So we're adding hydrogen to it. So the Linder catalyst, right? Hydrogen Linder catalyst, or we could use, there's another one. PT or PD, that's right. Or we could use platinum or palladium, right? So platinum or palladium, or we can use the Linder catalyst, okay? So then that would give me, go from triple bond to double bond, okay? Now, if I add hydrogen bromide, then I will get the what's it called? What is that process of the addition of alkanes to a thing? Alkane what? Yes, or it started with not alkenes. The addition of not alkanes, but adding halides to. But it's true. It's halogenation. Yeah, so you're just adding a halide to it. Yes. So it's just telling you adding a halide to it, right? Okay. So, but that's it. So we've done this reaction here, right? We've done this reaction here, and we've done this reaction here. So what the key is that if you're going to break it down to the steps, right? Steps of forming each of the ones. Does that make sense? Yeah, no, maybe. Yes, and so this is the concept of a multi-step reaction, okay? Okay, so if we're going from this acetylene molecule to and another hydrocarbon that's attached to bromine, what do we need to do to get to here? What are the steps to get to this point? Okay, that's right. So we see the triple bond, and we know that in here, these are all single bonds, right? So how can we get to this guy from this guy? So what are going to be my starting components? So let's try to work our way backwards, right? So if we started from here, because you already said we're going to have, we have a triple bond, right? Did you say that? Let's see, hold on. My pen. So if we can start from here and we want to get to there. So what would be a molecule doing retrosynthesis? So obviously you're going to say we're going to have triple bond something, right? Okay. So we know that if we're smart, we're going to end up with something like this. Okay. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2. Okay, good. Okay. So we're going to end up with something like that, right? Actually, it should be a double bond. Triple bond. 1, 2, 3. That's H2. Then that has to be a double. Okay. Is that right? Count them to be sure. Make sure I'm not wrong. So we have this carbon. This carbon. So that's 1, 2, 3, 4. 1, 2, 3, 4. Yeah. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Oh, yeah, triple one. There you go. So, 3, 1, 1. Okay. Okay. So then we end up needing a triple bond there, right? So how can we get from this, and what will be the next structure that we get? Working backwards. We're working our way backwards, right? So dimethylheptane, right? So 1, 2, 3, 4, 5, 6, 7. We know that, and we want to know, this is what we're going to be starting out with, right? Something that looks along something like this, right? At the very end. Okay, so how can I get from here? What would be my next product? Working our way backwards. How can I end up with adding a hydrocarbon, this group of hydrocarbons on one side? What do I need? I use the sodium amide to get us there, but what would be the product? What would be the starting material, the reactant, so that we can get this? Isobutane, okay. Are you sure isobutane? Okay, so you need an isobutyl. Okay, so then that's 1, 2, 3, 4, 5. So would that be an isobutyl? Okay. Am I in the way? My head's in the way. So that's, okay, so we have, on this chain, we have 1, 2, 3, 4, 5, 6, 7, right? That's the main chain. We have methane up here and a methane up here. So where can I split it up? So we know that what happens if we use, you said, the amide, what is that going to do? That's going to give us, if I remember correctly, we're going to end up with triple bond, C, minus, and then C, and then we'll say R, right? Okay, so where's the triple bond at? It's right here, right? So then one of these guys is going to be that. It could be this guy, or it could be this guy, right? Okay, oops, sorry, including that part up there, okay? Does that make sense? Okay, so then that means that, because we know that the part that we're adding on to this, circle around that, the part that we're adding on to this, right, has to be attached to a bromine, right, or chlorine, okay? So then that means that R is going to be the purple, and then this here is going to represent the yellow. Is that right? Okay, so then for this guy to happen, we know that this guy has to be, it's going to be here. And I know I'm running out of room, so I'm going to have C. Yeah, it could be either one, either or, yep. And then the other molecule is, got to put it in a different color to make it a little bit easier for us to see. So, okay, that is not pretty. So in other words, where's CH3? Okay, see? So that's one possibility, or like you said, we could switch it around where we had this one, and then the smaller part would be this one over here. Okay. Okay, so then that gives us these two molecules. Then we can go back even further because we know that to get from that initial one. Okay, so to get from here, we could actually use this molecule here. So we have these two options, right? We have an isopropanol bromide or an isobutanol bromide, isobutyl bromide. Okay. How are you guys doing so far? Okay, so what about this one here? So how can we get from the one, so that's cyclohexanol, acetylene to cyclo, what is that, 1, 2, so that would be ethanol. So 1 cyclo, 2 cyclo, hexyl ethanol. So how can I get there? So how can I get from a triple bond to an alcohol? Can I ask you one question? Start off here. Am I gonna have an enol form? No. Why won't I have an enol form? That's right, because my end product is not a ketone. I want an alcohol. So I know I can't have an enol form first. So that means I'm not going to have a double bond and an alcohol together, right? So that means that stepwise, I need to go to what? If I'm working my way back, work my way back. So what do I need? So we know that it can't be an anol. So it has to be, can it be an alcohol? Well, we already have an alcohol. Starting from an alcohol, we're working our way back, right? So we know it can't be an anol. So we know that it won't have a double bond in it here. So what is it going to be instead? It's not going to be an anol. So it's not going to be a double bond and an OH. It's going to be just a double bond. So we know triple bonds here. So then we're going to have this structure here. 1, 2, 3. Okay. 1, 2, 2, 4. Okay. You guys with me so far? So then we're going to have, working our way back, we're going to have a triple bond, right? So we're just going to erase this and go straight to the triple bond, right? Okay, so now that's retrosynthesis. So how do I get from triple bond to double bond? First, you got to create the triple bond. What is that process? Starts with an H. The reaction calls H2, that's right. So we have that first step. Let's see, different color. So we know if we're going from here to here, this guy is H2, what? That's right. Then catalyst, cat. Okay. Okay, so then that gives us our double bond. Okay, so then how do we get from our double bond to the B? What was that? No, you're right. Boronation. Okay, so we're going to use the boron, so BH, H3, THF. And let's see, then the second part would be to get the OH. H2O. Okay. Yep. Yep. Hydroxide, yeah.
Is it saying like the process that it's going through that reaction?
No, you're making sure that you have a base and peroxide and water. All those have to be present for it to react. Okay, so that's how we end up getting the OH on there. Right? And you end up with, because these guys are acting as a catalyst to get it started, except for the OH. The OH is being provided for the OH on the molecule. So the hydroxyl group, yeah. But you need them all present to kind of get it stable, because if you only have just the OH, it's not going to be strong enough. Because remember, the OH isn't strong enough to make it happen on its own. It needs that little bit of help. Yeah. Yeah. So, but you're talking about the amide. Is that the one you're talking about, the amide? So then we know that the amide, it had nothing to do with the ketone being formed, but the amide has to do with what forming? The carbon anion, right? So we want to form that carbon anion. That's when we're adding on carbons to it, right? In this case, are we adding on any carbons to this? No. So there's no carbons being added onto it. So we're not adding carbon chains onto it. Okay. So the only time that you use that is if you're going to be adding carbon chains to a triple bond carbon. Right? Okay. Does that make sense? It'll all start clicking, you know. Okay, so this is just showing you that process in a nice, clean format. But I wanted you guys to work it there. Okay, so let's try one more. Come on, we got this. A few more. Maybe. It lets me. Come on. Okay. So here's a good one. So if we're going from a acetylene to E2 pentene. Those ones that should be ingrained in your head, right? My ears hurting. Okay. So you said sodium and something liquid. Sodium what? So, but let's work our way back. Like we're doing the retrosynthesis. Come on, retrosynthesis. Okay, so first step. Let's work our way back. So we're going here, starting here. Working our way back. What are we going to have? How can we get? Because think about this is an acetylene, right? So how can I get it so that it's, because this is 1, 2, 3, 4, 5 carbon, right? A 5 carbon chain, pentene. So how can I go from acetylene to a pentene? Okay, so then how can I get from this to that? Ooh, this is a tricky one, right? Actually, getting ahead of myself. There's one more step. Ooh, come on, you guys got this. Think about what we've done in the past. We've got one more step. What we've done in the past. So how can I end up with triple bond being in between? You said what? So you said acetamide, sodium amide. Okay, so the sodium amide is going to cause us, but how can we get, because look where the carbon's at, right here. So we have a carbon and a single bond here. And we have a carbon and single bonds over here, right? So your triple bond is in between. It's in between. So how can I get from an N carbon terminal or like terminal to a center? Okay, so then you're right. So then we need to get from, we'll have C, H, 3, H, 2, C, triple bond, C, H, oops, not 2, just CH. And then, how do I get from there to there? Okay, so that would be my retro reaction, all right? Okay, so first step, from here to here, how do I get there? Yes, that's right. So let's draw this in orange. So if we're going from here to here, we're going to get alkylate, okay? So let me type it. Okay. Okay, so what causes alkylation? Sodium amide. Okay. Sodium amide. So we have and what else? What else do we need? What was it? Sodium amide and because what does sodium amide do? Because does that cause alkylation? No, it doesn't. That's only part of it. It only does the first part. That first part is done what? What is the first part? It what? Forms the ion. That's right. It forms the anion. Okay. So that's what the sodium amide does. Now, then what causes the addition? And what would it be in this case? What are we adding? 2. Oh, we're adding 2 carbons, so it'll be CH3, CH2, bromide, right? That's horrible, I know. My 3rd grade handwriting. Yeah, you could use chloride too. Bromide works best because it's bigger, right? And so it's more, okay, we'll get rid of it. Chloride works, but fluoride works too. They all work, but bromide works best. It's more efficient. Okay, so then that gets us here. So that's first step. Okay, so then what's going to get us from here to here? That's right, same process. That's right. And then we have CH3, Br. Okay. And then what's going to get us from here to here? Trans versus cis. Sodium, but it's sodium what? Was that? Yes, it is the sodium ammonia. That's right, the sodium ammonia combo. So you're right, sodium ammonia liquid at 3 at, and then we have to put liquid. Well, we know if it's at room temperature, it's a gas, so it's not at room temperature. Negative 78. Okay. Good job, good job. Yes. Not. So sodium not just means that they're making reference to sodium as a metal that is cooled. Okay. Okay. And so that's that whole concept of it being chilled at standard state. Okay, questions, concerns, Cash, Kool-Aid. Are you guys getting this? You feeling it? You said, yeah? Or did you say, nah? What time is it? Failed I asked. Okay, so we're going to stop 20 minutes early. Is that okay with you guys? We're going to argue. We got one more to go over. We'll go over it next week, but we're starting chapter 8 next week. I may give you guys another version of it if I get a chance to get to it. It all depends on how this week goes, which is going to be cray. Okay, I'll see you guys on Wednesday.